it's very nice to be here. Yeah, so today's talk is going to be very introductory. I'm happy to go into a bit more details in the question time or offline at some point. And the idea is I will try to give you an overview of what conditional logics are in a very specific framework. And then how can we construct proof systems for conditional logic? Again, using this labeled formalism, so a specific kind of proof systems for specific kinds of conditional logics. This is what I'm going to present is actually outcomes of research I was doing during my PhD, which was a joint degree between Marseille and the University of Helsinki. So Sara Negri and Nicola Olivetti here were my co-supervisors for the thesis. I still work and I'm still interested in conditional logic, so but this is just the easiest thing to present, and yeah, I hope it will be helpful to you. Okay, so this is the plan. I will first discuss what are conditionals in natural language, what I mean by conditionals at least. And then we will go into a bit more details. We will see what are conditional logics. And so the approach that we're going to be taken is going to be the approach proposed by Lewis and Stolnecker, and then continued by many others. So conditional logic as a kind of modal logics and conditional logics for which we can give a possible word semantics or Kripke semantics. And then in the final part, we will look at our labeled systems for conditional logics. I'm happy to be interrupted. If I don't get to the very end of the talk, it's not a problem, so feel free to ask questions whenever. Okay, so first, well, what are conditionals? What I mean by conditional is just any kind of if-then sentence. And for this talk, we are going to be interested in some specific kinds of conditionals. Maybe the most important are counterfactual statements. So you have a couple of counterfactual statements here. What if I had some ice cream? Wouldn't that be awesome? And then you also have another one. Maybe if I had a knife, I could cut our way free, things like that. So basically, a counterfactual is a sentence which describes a state of affair or the consequences of a state of affair which didn't occur. So more famously, you have the kangaroo example is from Lewis, David Lewis. So if kangaroos had no tails, then it would topple over. You have a whole bunch of more historical counterfactual. If Nixon had pressed the button, there would have been a nuclear apocalypse, so on and so forth. So these are basically the main kind of sentences that we're going to use today. And observe that this can also come in a kind of an epistemic flavor. So sentences such as, if Sam saw a lunar eclipse, then she would no longer believe that Earth is flat. So this is still a kind of a counterfactual, but we are also discussing the belief or the conditional belief of agents. So this is one. And then another kind of important sentences we're going to cover today are non-monotonic statements that are also of the form if-then. So consider the following. I can say also this is a very well-known example. I can say if Tux is a bird, then Tux can fly. But then maybe I happen to learn that Tux is also a penguin. And now if Tux is a bird and a penguin, then I would like to infer that indeed Tux cannot fly. And so this you can think of expressing as an if-then sentence, where you can say, oh, well, normally, if Tux is a bird, then Tux can fly, or normally birds can fly. And well, as we're going to see, the framework, the family of logics that I'm going to present will be able to cover both these case studies, so both counterfactuals and kind of non-monotonic statements. And of course, possibly many other kind of sentences that I'm not really describing today. Okay, well, as I guess you will know, if you try to use material implication to formalize counterfactuals or these non-monotonic sentences, well, things don't go so well. And the reason is quite simple. So if you consider a counterfactual, well, and you try to interpret it using material implication, then what happens is that just every counterfactual will be given the truth value 1, because of course the antecedent is not true, the antecedent didn't happen. And while a counterfactual, if I had some ice cream, then life would be awesome, this is probably true. It's easy to imagine counterfactuals where instead we might want to give them some truth values. So some counterfactuals are going to be true and some are not. So material implication is clearly not fine-grained enough to allow us to distinguish between various kinds of counterfactuals. And similarly, if you think of your non-monotonic sentences, well, classical logic is monotone. So if you have that A implies B, if Tux is a bird and Tux can fly, whatever new information you add to your antecedent, C, Tux is a penguin, you will still derive B. So you will still derive that Tux can fly. So this framework is also clearly not rich enough to express monotonic statements, no monotonic statements. Okay? So what we can do? Well, there's a number of different approaches that have been proposed in the literature to kind of remedy the paradoxes of material implication, or some paradoxes of material implication. So quotability theories of conditionals, I've put it here because it was probably the first one, but I don't really know what happens here. Probabilistic models, where you assign probability to statements. Belief revision, this is to account for revision of knowledge, kind of as in a non-monotonic statement. Causal model, and then this is the approach that we're going to follow today, possible word model, or a possible word approach to define a more fine-grained approach to conditionals. And so this is the people who initiated this approach are Stolnaker and Lewis, depicted in the picture. But then, of course, a lot of other people followed. Knuth, Cellas, and Burgess are only kind of the first one in the literature. So we're going to go for this possible word approach to conditionals. And what does it mean? And this is maybe the most important thing that I hope you will remember from the talk. So in this approach, what are conditionals? Well, they are a kind of modal operators. And so they behave like modal operators. So even the proof theory, when we are going to look at the proof theory, what we are going to do is we are going to look at the proof theory of modal logics. It's a well-developed field, and there are a lot of ideas that we can then hope to use in the framework of conditional logics. So in what sense conditionals are modal operators? Well, I'm sure you're familiar with modal logics, classical modal logic, where you just take a propositional language and then you add in your modal operator, the box. And then, of course, you can also define the diamond. Well, similarly, in the conditional logics that we're going to look at, you take your classical propositional language, and then you will add in a modal operator that I will denote like this. The difference being that it is a modal operator that takes two arguments, so it has an antecedent and a consequent, while the box here is unary. And it is worth noticing that both the box and the diamond can be defined in terms of the condition. So if I have a language with the conditional, I can retrieve box and diamond modalities. But of course, I cannot do the vice versa. So in my language with box, even if I have box and implication, I still cannot define the conditional operator. So the conditional is strictly more expressive than the box modality. So that's the idea. And these are going to be all the conditional logics that I'm going to discuss, or not really all of them, but so it's a big family of conditional logics. And actually, it's not even all of them. There are some other conditional logics down here that I haven't included. So the way to read this picture, you will see this picture quite a lot in the talk, is, oh, I see a question.
Yes, Mariana,
Yeah.
sorry. Can you give me an intuition in the previous slide? Maybe it's trivial, but can you give me an intuition of the definition of box in terms of negation conditional?
Yeah, so think of this maybe as a counterfactual, that's the simplest. So as a counterfactual, this would say, if not A were true, then bottom would be the case. So it can never be the case that not A is true. In every possible
Yes,
word
thanks.
that were not
Perfect.
true,
Yeah, makes sense. Thanks.
bottom, and therefore A is always
Thank you.
as well, I can maybe remark on this when we look at the semantics that comes in a second. When you evaluate the conditional, you will look at specific words. The box, of course, you look at all the words again. Yeah. So our logics. So the way to read this picture is I just arrange the logics according to their strength. So PCL for preferential conditional logic. And this is going to be the basic logic for this talk. And it's a logic discussed by Burgess. And this is the logic you would use if you want to express prototypical properties or the non-monotonic sentences that I was describing before. So specifically, if you're familiar with the KLM framework, validities in this language correspond to validities in PCL, where in the KLM logic, you don't consider nested conditionals, while in PCL you can. So this KLM framework is a fragment of PCL. Then you have that arrows correspond to adding an axiom or adding a frame condition to the class of model that I will introduce in a second. So specifically, all the logics starting from V and then going well, in the upper part of the cube. These are Lewis's logics, so the logics introduced by David Lewis. V is the basic system, and then you have extensions. And specifically, VC here is the logic that Lewis recommended to express counterfactual. So that would be the logic to express counterfactual statements. And then, just to mention another significant logic in this lattice, you have VTA, and this is the logic for the conditional belief of agents that I was just hinting at before. But for this talk, I think we're going to mostly be discussing BC, just because it's the easiest. Here I've put the axiomatization, just for reference. Mostly, I'm not really going to discuss it much. So an axiomatization for PCL, the basic system, is defined by adding to classical propositional logic 2 inference rules and a number of axioms describing the behavior of the conditional. So maybe you can easily understand what happens in the cautious monotonicity axiom. So this is a weakened form of monotonicity. So if you have A conditional B, you are allowed to add the new information, but only if A conditional C also holds. Then what happens? To obtain V, so the basic logic in Lewis's system, you add one axiom to PCL, and then you have a number of other axioms covering all of the other logics in our lattice. I can let you stare at this for a couple of seconds more, but to me, these axioms are, I have to say, are quite unreadable. And instead, so the way I can make sense of these logics is by looking at the semantics. So let's look at the semantics. And again, we have different, so we are going to look at possible word semantics, like Kripke models. But again, there are a number of different kinds of Kripke models that have been introduced in the literature. So you have the selection function semantics introduced by Cellas. You can cover some of the logics with the selection function, but not really all of them. So the selection function semantics was originally introduced for a weaker logic than PCL. I'm not going to talk about this. Sphere semantics. Sphere semantics is the semantics introduced by David Lewis, and thus it covers all of Lewis's logic in a very natural and modular way. So V and all of its extensions up here. Preferential semantics. So this was originally, I think, introduced by Burgess for PCL. So it covers all of the logics in the lower part of the lattice. But then a kind of preferential semantics can also be defined for V. So these semantics actually can cover uniformly all of the logics. And finally, neighborhood semantics. Neighborhood semantics is going to be the choice for this talk. Again, it's not the only choice possible. And basically, neighborhood semantics is what you obtain if you weaken the sphere semantics by Lewis, removing the nesting condition that I will discuss in a second. And then you get a more general form of sphere semantics, which is nothing but a simple form of neighborhood semantics, of neighborhood models. And we're going to use this logic because one, so you can modularly capture all of the logics in this lattice. And two, with respect to the preferential semantics, it is kind of easier to discuss, or at least there's a bit less symbols in the definition of the truth condition for the conditional. So in this sense, it's quite nice to use if you want to define proof system and specifically labeled calculi. So, neighborhood semantics. So instead of giving you a definition that would be quite long, I'm just going to show you an example, and then I'll try to wave my hand and explain to you how this semantics can be adapted to all of the logics in the lattice. So I'm going to define neighborhood models for VC. So this is Lewis's logics, which is good to represent counterfactuals. And since we are in one of Lewis's logics, these neighborhood models are nothing but Lewis's sphere model. I just want to define a more general setting because in this way I can modularly capture all of the logic when I define the proof systems. So what is a neighborhood model, specifically a neighborhood model for VC? So it's composed of 3 elements. You have a non-empty set of elements, our words. And then you have n, the neighborhood function, which is a function which associates to every word a set of sets of words. The elements of this set, so the sets of words, are what we call the spheres or the neighborhoods. And then the whole thing, so this n of x, this is a system of neighborhood, or in this case, a system of sphere. And the only requirement we impose, the basic requirement we impose on the neighborhood function is that every neighborhood is non-empty. If a neighborhood exists, there needs to be some element in it, some word. And then, as usual, we have our valuation function to evaluate propositional formulas that I represent like this in my picture. So this means that Y satisfies P and Q. Now you can notice that the the system of neighbors that I've drawn here is quite peculiar. And indeed, this is because we are in logic PC. So we additionally require properties on the neighborhood function other than this emptiness thing. And specifically, what we require is nesting, the property of nesting, what I was discussing before. So we want that for every word x, for all the alpha beta is what I use to refer to neighborhoods. So every alpha beta neighborhood in the system of neighborhood associated to x needs to be, well, either alpha is included in beta or beta is included in alpha. So this gives us this onion shape setting in which we have that the spheres are concentric, one included into the other, within the same system of neighborhood. And second condition for C is the condition of centering. And what does it mean? Well, this means that for all x and for all the alpha in n of x, we have that x belongs to alpha and the singleton of x belongs to n of x. This means that the smallest neighborhood, or the smallest sphere here, is going to be a singleton word that contains only x itself. So for every n of x, the innermost neighborhood is the singleton of x. And what's the intuition here? Well, the intuition is that every neighborhood or sphere represents a degree of similarity with respect to the actual word. And the farther away you go from the center of sphere, the less similar the word becomes to the actual word. So if you fix x to be your actual word, then it makes sense that the word which is most similar to the actual word is the actual word itself, x. And then as you go to the outermost spheres, you will have words that are less and less similar to x. That's the intuition. Okay, so these are the models for BC. Yeah, question?
Yes, sorry. Do you have the valuation defined also on x? Or, I mean, in this example here, x, if there is nothing, it means that does not satisfy
any,
yeah,
neither P nor Q, yeah.
Yeah.
So
okay.
In this simple example, X does not satisfy any propositional atoms, but of course it could have been different. Yeah, good point.
It doesn't mean that you don't know. It means that you. I mean.
Yeah. It means it doesn't satisfy P, it doesn't satisfy Q, but we are in classical logic. So
okay, thank you.
Yeah. Other questions? This is probably the most difficult part of the talk. Okay, so how do we evaluate a counterfactual in this setting? So this is a truth condition. So let's try to make sense of it. Truth condition is, of course, general. I have fine-tuned it to this example specifically. And in my example, we have that X indeed satisfy the counterfactual P conditional Q. Okay, so X satisfies P conditional Q, so always think of the counterfactual interpretation. If P was the case, then Q would have been the case. If and only if, so for all the neighborhood alpha in n of x, it holds that, and then here I have introduced some additional notation. So if alpha existentially satisfies P, and this means that there is a word in alpha which satisfies P. So if there is some word somewhere that satisfies P, if this is not satisfied, it means that P is not true anywhere, and then the conditional is going to be vacuously true. It's an if then. So if there is some word somewhere which satisfies P, then there needs to be a word beta, there needs to be a neighborhood beta, such that beta is included in alpha, and such that beta also existentially satisfies P, so beta contains a word satisfying P, and moreover, beta universally satisfy P implies Q, and this is the material implication. So if P is true at some neighborhood alpha, there needs to be a smaller neighborhood beta, which also satisfies P, and such that all of the words in beta satisfy the material implication, P implies Q. This condition here is inclusion is not really needed if you look at Lewis's models. It's needed because we want to be general in this setting. We also want to cover the logics without the nesting. And so what is this saying? So I want to know whether if P was the case, then Q was the case. So the idea is I'm going to consider the possible word around X. So in this example, P is not true at X because, yeah, it's a counterfactor. So P is something that didn't occur. If I had ice cream, I don't have ice cream here. So what we do is we look at our spheres. We select a point somewhere where P is true. So in this case, it would be this Y here. And what we do, we check that in the same sphere, so in the same degree of similarity, and observe that this also includes all the innermost words, right? What we want is that in that degree of similarity, whenever P is true, Q is also true. So P is not true at X. What I do is I look at the closest word where P is true, and I check that Q, the consequent, also holds there. That's the general intuition. I have to evaluate a counterfactual. I cannot evaluate it at the actual word. I will go to the closest, more similar word where the antecedent holds, and I will check whether the consequent holds. Question, yes?
Yeah, just clarification. You have already pointed out that this is essentially a preferential semantics, as in the KLM thing.
Yeah.
Which I think actually was introduced by Shohan in his PhD thesis, 1988. And I was wondering if, so your sphere system here is one way of expressing in this case, total order, right? It could be partial.
Yeah.
And so is it just another way of saying exactly the same thing, or is there more information here that you can get from the topology of the sphere that you don't get from the just ordinal information you have in models?
Very good question. It is exactly the same thing.
Okay.
So Lewis already shows in counterfactuals how you can translate between sphere semantics and preferential semantics. So if you have a sphere model, you can construct the corresponding preferential model. You just define a preorder. So a preferential model will have a preorder among words, and then the spheres just give you the pre-order. And vice versa, if you have a preferential model, you can construct the sphere model. And basically what we had to do sorry, I'll go back. What we have to do here in this paper to define neighborhood semantics also for the lower part of the lattice here, we had to do the same thing for preferential models in which the order is not necessarily a total order.
Okay, so if I may just quick follow up, then it is a bit fun in a way, because the idea, sort of the pre-formal intuition of a counterfactual statement, to me, is not exactly the same as the intuition I have about the typicality assumption or the default assumption. So, typically birds fly don't seem to have a false antecedent to me. Yeah, but maybe this is
maybe this helps. So
Yeah.
the logic you would use to formalize these non-monotonic statements is not a logic where you have, it's not a logic here. This would be more PCL or maybe easy extensions of PCL. And what changes is nesting. So what would happen is that if you want to define a neighborhood semantics for the logics in the lower part of the lattice, you are not nested. So not all of the words would be ranked in this nice way in which you can exactly see which word is more similar to another one. So you have much more freedom in that. But if you think about it, the idea, I would say, is still somehow there. So normally birds fly would mean, well, you can check a set of prototypical words and you can check whether birds fly there or something like that.
Yeah, okay, thanks. Sorry, I didn't mean to interrupt this. Sorry.
Was there another question?
Yeah, but I answered myself, so thanks.
Oh,
Yeah.
okay, that's perfect. Okay. Okay, so this what I've presented here with nesting and centering are neighborhood model for one of the logics in the lattice. And now the idea is if you want to obtain, so nesting and centering are here, if you want to obtain semantics, neighborhood semantics for all the other logics here, you will just add combinations of the frame conditions. So all of these frame conditions are from Lewis, and then they can basically be adapted also to the lower setting here. I'm not really going to detail them also for the interest of time, I guess. But yeah, so it's kind of similar to modal logics. You specify additional frame conditions and you get a family of logics. Okay, so this concludes the first part of the talk. And now in the second part, I want to discuss proof systems, specifically labeled calculi for conditional logics. How much time do I have?
So I think you can go on up to 20 minutes.
Oh, okay. Then I don't have to rush too much.
Yeah.
I might also take a bit less time. Let's see. I'm super happy to be interrupted, so no worries. Okay,
thanks.
Okay, first I have to backtrack a bit because labeled calculi are a framework that you can define by enriching the Gentzen-style framework for classical propositional logic. So I just quickly introduce it, and then I will try to motivate why this framework is not enough for conditional logic, why we need a bit more than just the Gentzen-style calculus. So in usual Gentzen-style sequent calculus, the basic components are sequents. So for gamma delta multisets of formulas, a sequent would be something of this form, gamma sequent arrow delta. And to a sequent, there corresponds usually a formula of the original language that you will read as, conjunction of formula in gamma implies material implication, disjunction of formula in delta. And then, of course, you can have many different variations of sequent rules for classical propositional logics. But the idea is, what you do is you will define rules that somehow decompose a main connective into its sub-formulas. And then a successful derivation in sequent calculus will look something like this, where you basically decompose your formulas until you get to your initial sequence, very, very roughly. So, second question is, why are we interested in sequent calculus at all? Or why am I interested in sequent calculus at all? Why do we want to define proof systems for conditional logics, for instance? The main idea is if you have a sequent calculus, then the sequent calculus can help you establish a number of different properties about the logics. And well, what I'm particularly interested in is decidability and finite model property of the logic. And what does it mean? Well, suppose that I want to answer the question whether a certain formula of a certain logic is valid. And then if I have a sequent calculus, and if I have a sequent calculus with certain desirable or nice properties, then what I can do is I can just run the proof search for my formula A, and then at some point I will stop with something that is either a derivation, so a successful derivation of my formula, or something that is a finite object, but it's not a derivation. So at some point I stop and, well, I just declare failure, which means that I usually have an axiom to which I cannot really apply any more rules. Or I have some kind of loop check that tells me, oh, here you can stop. And usually the nice thing is that if proof search fails, you might want to extract a counter model from the proof search itself, from one branch of the proof search. So you can use sequent calculus to implement decision algorithms for the logic. And for this, you want to have some desirable properties of your sequent calculus. Maybe the first and most important one, you want your cut rule to be admissible. You don't want the cut rule to be an explicit rule of your system. And why? Well, because if you're doing a proof search, so you start from the bottom and try to construct your proof tree, whenever you apply a cut rule, you have no idea what this formula A could be. So you have to guess what your formula A needs to be. And so clearly this disrupts your mechanism in which you kind of automatically try to build your proof from bottom up. Another one is a bit more technical, invertibility of the rule. This means that basically when you go from conclusion to premise, you don't really lose information. Termination is important. If you want to have a decision algorithm, you want your proof search to stop at some point. And then, yeah, it's nice if you can construct a counter model from failed proof search. So this is not the only use of sequent calculus, but this is, I would say, one of the important ways in which sequent calculus can be used. And as you can see, it kind of gives you some hints on which kind of rules you should define for your proof system. So if you try to, you can try to define a sequent calculus for just modal logics. As I said, conditional logics are a form of modal logic. So by looking at what happens in the modal setting, we can get a lot of information about what should happen in the conditional setting. So what you would do is you would just add a box rule. I'm not really going to discuss this rule much to your sequence system. But there are some problems. Okay, so first, the rule is not invertible. The gamma and the delta I lose when I go to the premises. And even more importantly, not all the proof systems that you can define in this way are going to be analytic. And specifically, for instance, for modal logic S5, which is relatively simple and very well known, there is no known cut-free Gentzen sequent calculus. Which means if you want to define a sequent calculus for S5, you will need to include the cut rule, and you have no way of showing that it is admissible. So in this sense, sequent calculus for modal logics has some limitations, specifically if you want to implement a decision procedure for it. And in the literature, mainly two solutions have been proposed. One solution is to enrich the language of the calculus, and this is the labeled approach, of which I will say something more in a second. And the second solution, which I will not discuss today, is instead to enrich the structure of the sequence. And here you can find things such as hypersequence or nested sequence, where instead of your sequence is not just going to be multi-set of formula in the antecedent, multi-set of formula in the consequent, but in hypersequence you have a multi-set of sequence, and in nested sequence you have this thing is basically encoding a tree of sequence. So you can encode both approach, enriching the language or enriching the structure, are way to have much more information in your sequence than you would with a Gentzen-style sequence. So today we're going to discuss a bit the labeled approach, and we are going to see how to adapt it to the case of conditional logics. Yeah, both approaches can be adapted to conditional logic. So again, let me shortly describe what happens in the labeled calculus for modal logics, and then we go to the conditional case. So, labeled calculi for modal logic. So the idea is we enrich the language, and what we're going to do is we're going to first add a list of countably many variables for words, x, y, z. And these are going to be what we call the labels. And intuitively, these represent words for a Kripke model. So we enrich the language with some syntactic information, labels, that represent some semantic information. So there is a very clear link between what happens in the semantics and what happens in the rules of the calculus. So we fix our variables for words, and then instead of operating on formulas, our labeled calculus is going to operate on labeled formulas. Labeled formulas are of two kinds. So you have these things that we call relational atoms, x, r, y, and this intuitively means, well, x has access to y. So it's describing the accessibility relation of Kripke models. And then you have labeled formulas of this sort, x in column A, which you read as x satisfies A. So already from here, you can see that basically my labeled formulas can encode all of the information I need from a Kripke model. I can talk about the accessibility relation, and I can talk about satisfiability or unsatisfiability of formulas. Then a labeled sequent is something of this sort, where gamma and delta are multi-sets of labeled formulas, but not relational atoms. And R here is a multi-set of relational atoms. So relational atoms are only in the antecedent of my sequent. And just to give you an example, these are the rules for box. If you remember the truth condition for box as at Kripke models, box A is true in X if for all the words Y's that are accessible from X, A is true at Y. And basically this truth condition is just spelled out into the rules for the box operator. So for instance, if you look at, this should be the right rule and this should be the left rule, of course. I mixed up. But so if you look at this rule here, which is the right rule, so what this rule says is, okay, X satisfies A. What does it mean? Well, it means that for any word Y that is accessible from X, then Y will satisfy A. Where this Y exclamation mark, this is a side condition which signifies that Y is fresh. So Y does not occur in the conclusion. So it's kind of similar of what happens with the quantifier rules in the sequent calculus for first order logic. What happens to the for all on occurring in the conclusion? Well, then you want to instantiate it with some fresh variable that you have not used before. And this is the same thing. And this other rule is just a dual. So here I will take any Y that are accessible from A and state from X and state that A is true there as well. So it's just a syntactic way if you want to reason about models and to reason about truth of formulas in the model. Oh, sorry. And the other nice thing about labeled calculi is that they are an extremely modular framework. And what does it mean is that, for instance, if you think of the modal logics cube, once you define the rules for box and possibly for diamond, then you can cover extensions of K just by adding rules that operate on the relational atoms. They don't really touch the formula, but just the relational atoms. So for instance, transitivity, well, the corresponding rule would be this one, where I add that Z is accessible from X. So it is very easy once I have defined the calculus for the base system, it is very easy to add rules to capture other frame conditions. Okay? So the idea is we are going to now use these tools to define calculi for conditional logics. Now, again, we are going to enrich the language, and then we're going to define our truth condition. Well, sorry, we're going to define the rules for the conditional just by looking at the truth condition. So the way we enrich the language now is going to be a bit different because we're not really looking at, well, we are looking at relational models, but we have this neighborhood function on top. So we have to talk about this neighborhood function into the syntax of the calculus. So as before, we start with countably many variables for words, but now we will also have variables for our neighborhood. And the relational atoms, well, now we will have things that talk about neighborhoods. So we will have things such as X belongs to A, X is an element of A belongs to a system of neighborhood, of N of X, A included in B, and that's it. And what about labeled formulas? Well, we will have things such as X satisfies A. And now if you want, here comes kind of the drawback of this proof system because, well, we need to express this truth condition into rules. For the box, it was easy. It was a very easy truth condition. A left rule and a right rule were enough. Here we are looking at a much more complicated condition because there's a for all, there's an implication inside, and then within the conclusion of the implication, we have an existential. So the idea is we cannot hope to express this with just two rules. We need many more rules. What we are going to do is we are going to decompose this truth condition in various different parts, and then we will treat them separately. So this means that I want to have labeled formula talking about these things. Here is the same notation to be suggestive, right? So this means that A is satisfied as some word of the neighborhood. Similarly, for the universal quantifier, A universally satisfies a certain formula A. And then you have this kind of horrible thing, which is just taking care of the whole of the conclusion of my implication here. So this is nothing particularly significant. I just have to, I need a way to decompose my truth condition, but it does make the calculus kind of unreadable. So I'm going to show you some rules, not all of the rules, because that's probably a bit too much. But so the idea is the same. So we are going to use, so these are just some of the rules. I have the rules for the conditional. Propositional rules, of course, remain unchanged. I haven't shown them, but and for the conditional, well, you are just going to decompose the truth condition. So you will introduce a fresh alpha, for which you will say, well, if A existentially satisfy the antecedent of the conditional, then the conclusion of the conditional, of the truth condition, should also hold. It's a lot of relational atoms. And then here, you will also need to have rules for the second part of your truth condition. It's not difficult, but it's very difficult to see it at play in such a short time. But trust me, what we are doing is we are just expressing the truth condition in the form of labeled rules. And well, the nice thing is that similarly as what happened in the case for modal logic, we can then easily add rules for framed condition. So once we define the proof system for PCL, of which this will be some, not all of the rules, then just by adding rules for frame condition, you will get all of the proof system in the big lattice that I shown before. So for instance, if you want to have centering in your labeled proof system, then you will add a rule saying that, oh, if A is a neighborhood in n of x, then the singleton of x should also belong to n of x and should be the smallest. And then you might need some rules to discuss the behavior of the singleton operator. And even more rules. So this is a substitution rule. Whenever something is in the singleton of x, then it will satisfy all the atomic formulas that are true at x, will also be true at y. Properties of singleton. And then this is how a derivation would look like. Derivation tend to get extremely long, so the dots are to make it fit into one page somehow. But the idea is, so this is the axiom for centering. And the idea is I just apply my rules. In this case, I also need to apply some of the rules for the extension that I very briefly showed before until you get to an initial sequence. So it might be difficult to define the rules, but then their application is quite easy, of course. What we have as main results? Well, we have soundness and completeness. To prove soundness, you have to do a bit of work. I'm not going to show any of the proofs, don't worry. But if you want to prove soundness, your sequence don't really have a formula interpretation in the logic because of all the labels that you have added. And so to prove soundness, you have to define an interpretation of the sequent within neighborhood models, but then it's quite routine. And to prove completeness, well, one way to prove completeness is just by showing admissibility of your cut rule. And this is something that is quite easy, even though the rules look extremely complicated. Because, well, the rules are defined in a very symmetric way, so no problems with the cut. And the fact that the relational atoms are only in the antecedent of sequence, well, what we have is that they cannot be cut formulas. So the proof just goes through quite easily for all of the systems. And then what is interesting, exactly because we have a labeled calculus, is that, well, we can actually define a way of proving completeness semantically. Meaning that, well, you want to prove that if A is valid, then a sequent having xa in the root is provable. And what you would do, you prove the contrapositive. So if A is not provable, then we can construct a counter model for it. And since we are in a labeled calculus, constructing a counter model is going to be extremely easy. So a strong pro of a labeled proof system is that extracting a counter model is actually easy. But then, if you want your proof search to terminate, well, this is instead pretty hard because of all of the labels that might occur in your proof search. I'm almost done. Just one more observation, basically. So I said that we can learn a lot from conditional logic just by looking at the modal logic case. And this can be made precise in a quite specific way. So you can define a box operator from the conditional operator. And depending of the logic you are in, this box modality will have different properties. So this outer modal logic, the outer modal logic is the logic that you get if you define the box from the conditional, terminology from Lewis. And what you get, I hope this doesn't get too unreadable. These are the logic, these are the property of the box that you have once you interpret it using the conditional. So you have the PCL and V, the box that you can define there corresponds to modal logic K. They're always the same. You can look at either level, they are the same. With N, normality, you get T, VT, VC, and VW. Here you get modal logic T. And then here you can see this big block. These are the stronger system. These are S5. So kind of similarly as what happens in the case. So in the case of modal logics, you can define labeled calculi for all the logics from K to S5 modularly. And this is kind of similar to what happens in this framework. Using the labeled system, you can indeed define modular proof system for all logics going from K to S5, in a sense. It is also quite interesting to see. So remember this square here, VTU and extensions. So what happens if you think of different kind of proof system? Because I discussed the labeled proof system, but there are also different kind of proof systems that you can define. And then the situation changes. So in the course of my PhD, we can define this sequent calculi with blocks. Here you enrich the structure of sequence only for the red logic, so V, Vn, Vt, Vw, Vc. And then for these logics here, so those correspond to S5, you will need some hypersequential structure. So the labels give you modularity. It is possible to do different things that I will not present today. You will lose modularity. You might have a more economic sequent calculus, not so many unreadable rules, but definitely less modular. And there is no non-labeled proof systems for the logics down here, PCL and extensions. Okay, so this is my last slide. What I did in this talk, a very short introduction to conditional logics in the tradition of Stalnaker and Lewis. And then I tried to sketch how to define a proof system for conditional logics using labels. What I would like to do, current and future work, okay, so this I haven't really discussed the comparative plausibility operator, but it's another operator that Lewis defined and that might deserve some study on its own. Ceteris paribus counterfactuals I also haven't described. These are counterfactuals in which you specify some additional conditions that ought to be kept unchanged in the evaluation. And then, yeah, I'm quite excited about this, explore the proof theory of intuitionistic conditional logics. The logics have been defined, but there are no proof systems for it. And possibly also checking what happens if you take other approaches to conditional, so maybe beyond Stalnaker and Lewis, what happens on the proof theoretical side. So, yeah, thanks a lot.